very, very much for the introduction and the invitation to speak here. It's been a great pleasure to attend this seminar whenever possible in the past several years now. 6 years it's been running. Um, I'm going to talk about two joint works with Plamen, who is in the audience. That one of them appeared some years back, and the last one last year. So apologies if you've heard about this topic before. So the reason I'm talking about them together is that they kind of fit within the same theme, and it's kind of interesting to see how they compare. So basically, we treat two different nonlinear PDEs with sort of similar methods. And part of the take-home message is that in each one of these problems has to be treated differently because the behavior is quite different somehow. Let's see. So yeah. So the first one is the non-diffusive Westervelt equation, which looks like the usual wave equation that has a nonlinear term, which makes it quasi-linear. So we're taking two time derivatives of p square. I'm going to say more about what these things are later. And the other one is the Maxwell system with a nonlinearity of Kerr type. So this is the regular the regular Maxwell system, and we have certain constitutive equations that relate the electric field and the electric displacement and the magnetic field strength and magnetic flux density. And the point is that the polarization, so this P function here is which essentially tells you how the electric displacement is related with the electric field, has a cubic type nonlinearity. And because this is a first order system in the way it is written, that makes it into a quasi-linear system. So what we're going to be interested in is constructing highly oscillatory asymptotic solutions that explain the experimental observations, then justify those solutions and use them to recover the nonlinearity parameters alpha and chi3 here. So let me start with the first one. So this is the Westervelt equation in its more general form is a hyperbolic quasilinear PDE. And it is used to model the propagation of high-intensity ultrasound in a medium. It looks basically like what we said before. So it's a wave equation. There is a diffusive term, which we're not actually going to consider. And then on the right-hand side, we have a quadratic nonlinearity. Here, this P tilde denotes deviation of acoustic pressure from equilibrium. C is a sound speed. We're going to take this to be a constant. B is the diffusivity of sound. Alpha is dimensionless, and it's the nonlinearity coefficient, which we would eventually like to recover. And rho naught is the average density of the medium. So it has applications mainly in imaging, lithotripsy, thermotherapy, and others. I'm not an expert, but I like including cat pictures if I can whenever I give talks. So here are some cat pictures. So I'm going to mention some simplifications, mainly because they're going to come up in our analysis later. So if we're looking at a pulse sound beam that is propagating in one space direction, if you write it in terms of retarded time, then there are certain simplifications you can consider. And then, after a bit of massaging, you obtain the Burger's equation, which is viscous if you assume initially that you have diffusion, or the inviscid if you don't. So if you assume that this B is zero, so you have the wave equation with just a nonlinearity, as we mentioned at the beginning, then what you find after these simplifications is the Burger's equation. And you might know what the solution looks like from PDE courses. So if you start with with a sinusoidal wave like this, what happens is that when P is positive, then you tend to move towards the right, whereas if P is negative, you turn to move towards the left. And so this equation models basically a wave that is breaking at some point. So at some point, you obtain a singularity in your solution. Okay, so that's gonna appear a bit later. But so let's look at the non-diffusive Westervelt equation. So here we're going to have a non-negative, compactly supported nonlinearity parameter. We assume as before that the B is 0, and here alpha lives inside a ball in Rn. So what we want to do is we want to probe the medium with certain asymptotic solutions, which are given by a superposition of high-frequency waves. So we're going to have a bunch of waves of this form. Here, those waves are periodic in the last variable. This is 2 pi periodic. And h is thought of as a small sort of parameter. And the phase has to be determined. So if you're in the linear case, if you have the alpha to be 0, then regardless of what the k is, the phase satisfies an econal equation. And, this is a very classical econal equation. And U naught satisfies a transport equation, which is also linear and homogeneous. The coefficients of the transport equation depend on the phase function that we determined in the step before. And then for j greater or equal than 1, the UJs satisfy transport equations with sources that depend on phi and on the previous profiles that we have already constructed. So this is sort of the general theme of how this goes. Now, in the nonlinear case, the choice of k actually affects the qualitative behavior of the solutions. So if you look at the derivatives of the expressions UL in this ansatz that we had before, when you hit this object with derivatives, then you obtain negative powers of h, which is also a feature of the linear case, but then if you have a nonlinearity, then powers of h can be multiplied together. And so this actually changes the behavior. So if you rewrite the Westervelt equation, bringing the highest order derivative to the left, then you can observe that if your amplitude is too large, so when k is equal to 0, for example, then the nonlinearity actually might affect the econal equation that determines the phase. And that could lead to very complicated behaviors where the econal equation is actually coupled with equations for the profiles, and you can't solve them separately, which would be a really bad thing. And you might even fail to be hyperbolic. So if P is big, you can see that in principle this coefficient here could vanish, and then you lose the hyperbolic character of the equation. On the other hand, if the amplitude is too small, so if you take a very large k over here, then the effect of the nonlinearity is essentially pushed to very high order terms. And basically all of the profiles satisfy linear transport equations, which some of them eventually might depend on the nonlinearity, but at least we don't see the effect in the leading orders. And so the question is, what is the correct regime? So the regime that corresponds to the power k is equal to 1 is referred to as the weakly nonlinear regime. This is a traditional term, and it generates the consistent behavior with what is observed in propagation of ultrasounds. So what happens is that in that case, the econal equation stays the same. So the sort of the geometry of the propagation does not change. And so, you can still consider the typical sort of phase function that you consider in the linear wave equation Rn. And the effect of the nonlinearity is seen in the transport equation for the principal amplitude. And actually, the principal amplitude satisfies a Burger's equation after you integrate it in theta. It satisfies a Burger's equation which we saw before. So we actually see that this simplification that we mentioned in the beginning, which can be justified with some heuristic arguments, actually here appears in the asymptotic analysis of the profiles. And then once you go to the next profile equation and all the ones after that, they're all linear. And I mean, of course, they're going to depend on the nonlinearity and on previous profiles, but you can solve them sequentially. And so you see that essentially the only possible bottleneck in solving your profile equations is is this equation which is nonlinear, and in principle it could create a shock. So essentially the idea is you have to choose your initial data to make sure that you don't run into trouble. So if you consider initial data which is highly oscillatory, and as we mentioned we want the amplitude to be O of h, then you assume that initially you're supported somewhere away from your nonlinearity. And well, you also have to fix the velocity at time zero. And so the way we do this is we pick that to be zero, which has the effect of generating two waves. One goes in the opposite direction. And this is just a technical tool somehow. This is not really important. It's going to go outside of the nonlinearity. We completely understand how it behaves. We really care about the one that's going into the nonlinearity. And so once we choose our data like that, we get two waves propagating in opposite directions. And if we're able to solve the transport equations that we described in the previous slide, then we can construct a full asymptotic solution. So essentially the only possible problem is the first one. And it turns out that you can actually write a fairly straightforward condition that tells you that, if you satisfy, if your initial data has a small enough maximum, then you can guarantee that basically you're not going to develop a shock. Okay, so this was about asymptotic solutions. Now, geometric optics have been studied by many authors already since the early 90s. Oops, sorry. And some of the solutions are asymptotic. Some actually develop techniques for justifying them, which is what we're going to use. So our solution is only formal until now. We don't claim that it approximates an exact solution. Now, the problem is that the classical theorems for the well-posedness of nonlinear hyperbolic PDEs typically require that your initial data are in a Sobolev space for a high enough order. And that typically depends on the dimension. You have some sort of Sobolev embedding to worry about. And sort of the time interval on which you can get existence and uniqueness of a solution, that depends on that norm. But for us, because we have this effect that we have these highly oscillatory solutions, our data is not even bounded in H2 as H goes to 0. So that the H2 norm of our initial data blows up for H small. But it turns out that there is a result by guess which proves the existence and uniqueness of exact solutions, so symmetrizable hyperbolic systems, and we can apply his theorem. And so basically we can convert our asymptotic solution to one for such a system and obtain existence and uniqueness. So our theorem says that if you assume the condition I mentioned before to make sure you have no shock, then for a priori fixed amount of time, you can solve the Westervelt equation, and you can make sure that its L infinity norm is small enough that the equation stays hyperbolic. And moreover, you can actually decompose the solution in a sum of a P plus and a P minus, where, as we mentioned, so P minus is propagating away from the nonlinearity, so we're not going to care about it very much. And P plus propagates into the nonlinearity, which is the part of the equation that we care about. And so that one, we can actually tell that its profiles look like, at leading order, a U naught that satisfies the Burger's equation. So we actually have a fairly good understanding of what the leading order should satisfy, up to an error which is in a certain space. So if you want to look what this looks like, so you send your you start with some initial data. It splits into two parts, as we mentioned. One goes into the nonlinearity, one goes away, and it goes into the nonlinearity. Something happens, and something exits on the other side. So if we want to look at what happens, you can take a look at these wave packets. So on the left above, we have a linear solution. So with the nonlinearity is 0. And below, we have a nonlinear, we actually have the nonlinearity activated. So what happens is that, here the red is the maximum, it's like the positive part, and then the blue is the negative part. And so we see that compared to the linear case here, the red is moving faster, whereas the blue is lagging behind. And this is exactly the behavior that we see in Burger's equation on the right. So this kind of justifies the data. This tells us that this was the correct regime. And then the inverse problem has to do with recovering the nonlinearity parameter by measuring the waves after they have interacted with it. So this has been a very active area of research in general, nonlinear waves for the last 10 years or so. After the pioneering paper of Kurilev, Lassas, and Ullman, published 2018, there has been a lot of activity in the topic, which mainly uses this the high order linearization method, in which you use the nonlinearity as a tool, and then you collide waves to obtain information about your nonlinearity. So here we're not using linearization, essentially. We're using asymptotic solutions. In the Westervelt case, there has also been quite a bit of activity, also until very recently. Mentioning some names here, there is much more, and apologies if I have not listed your paper. And so I think most of these papers use high order linearization, at least definitely some of them. But there has also been some work in the same spirit as what we're using today. So using geometric optics, there are some works of Antonio Sabareto and Stefanov, and there's also a recent work by Nathan Sabareto from 26. But this is for semi-linear hyperbolic PDEs. And so the theorem says that if you assume the conditions in the previous theorem, so you assume that your initial data is such that you get no shock in your Burger's equation, then you wait for long enough that the rays starting at the support have exited the support of the nonlinearity. And then you can determine the X-ray transform in a certain direction. And then you can vary chi around, and you can move your initial data around and shoot them from different directions to recover the X-ray transform in different directions. And if you have that, you can recover the nonlinearity. So here the idea is that sort of you can compare a wave packet corresponding to the nonlinear equation with a wave packet corresponding to the linear equation, so with the nonlinearity being equal to 0. And it turns out that the horizontal shift is actually proportional to the X-ray transform. So this is how you extract the X-ray transform from this information. Okay, so next we can move to the second equation. And so we're going to see that in a way the steps that one has to take are kind of parallel or very similar, but the behavior that you observe is actually quite different. And it's pretty interesting to see how different they are. So here we would like to model the Kerr effect, in which you have a material that on its own is not birefringent, but once you apply a strong electric field to it, then it actually exhibits birefringent behavior. So this model can be described with the help of the Maxwell system with the Kerr nonlinearity, which I mentioned in the beginning of the talk. So we have the usual Maxwell equations together with some constitutive equations that relate with each other the various quantities. And what we want to model is what happens in a Kerr cell shatter. So this is a picture of a Kerr cell. And so as a cartoon of the situation, so here is the cell. So this is this yellow liquid that we see in this picture. And so you place a polarizer on one side of your cell, and then you place a polarizer on the other side at 90 degrees. So the material is a material with high Kerr constant, they say. So it's typically nitrobenzene, or there's some other options that I forget. But so the point is that the light enters polarized, and because the second polarizer is at 90 degrees, nothing exits. However, once you apply a strong electric field, what happens is that the direction of the speed of propagation changes in different directions, and so the polarization actually turns. And if you arrange it well enough that it turns by 90 degrees by the time it has exited, then you actually see light. And I have a nice video of this, which let's see if I can show you. Let's see, sorry. I don't know how to do this. Sorry, Katya. Wait, no. So am I still sharing?
No.
I'm not sharing. Okay. I'm going to share something new. Wait a second. Okay. Now you should be able to see the video. So we have the light source on the left, and those are the polarizers. And we have the Kerr cell in between. Now we turn on the electric field and we see light. You turn off the electric field and you see nothing. This is the image from the camera after you have gone through the two polarizers. So the idea is that essentially you can use this and create a shutter that is much faster than a mechanical shutter, because it's by some sort of by an application of an electric field. Okay, let me see how I can go back to what I was sharing before. Here. Okay, good. Yes. So, okay, that was the idea. That's what we want to model. Now we can go about looking at the mathematical analysis. So we had this Maxwell equations with constitutive equations. We put all of them together, and we're going to, make a simplifying assumption that the first order of the polarization is zero. I mean, that makes the computations easier. We don't expect that it changes them in any sort of very meaningful way somehow. And that this is one. And so if you combine all of that, and you're going to see at the end that what you get is something that looks like a wave equation, vector wave equation, with an additional term here, which is a divergence term. And then on the right-hand side, we have this cubic nonlinearity. See that we have two time derivatives here. So as we expect, we should have a quasi-linear equation. And there was also a divergence free condition, which was here. And it takes this form. Now, an observation is that here that we're in this sort of nonlinear situation, the divergence of E is not zero in principle, so you can't directly get rid of this term. So this, if you had a linear Maxwell system, then this divergence would be zero. You could get rid of the term, but now you have to work a bit harder. So, okay, you can check that essentially, either you solve this system or you solve that system. Those two are morally equivalent. You can jump from one to the other. Okay, this looks too technical. I'm not going to spend too much time. And again, as we mentioned, what we want is now we want to construct solutions for this thing, and we want to sort of try to model the behavior that is observed in a Kerr cell. So if we have a no strong field present, as we mentioned, the wave propagates linearly. If we have a strong field, then the polarization should rotate. And what happens is that the relative change in the index of refraction for the polarizations that are parallel and perpendicular to the applied electric field, which is here sort of vertical, is proportional to the square of the amplitude. And so we expect to have a solution of this form that I mentioned before. So we should have a strong electric field, which we don't expect it to be oscillatory. And then we have the beam. So here we can be thinking of E as being the vertical arrows, and then U is sort of the solution that comes here. It's like the beam of light that passes through the cell. And the phase we need to determine. So what you observe is that the geometry of the rays is not affected. They still propagate straight, but the amplitude is. So if you consider a scalar toy model where you have this sort of cubic nonlinearity, and you do the same thing that we did before with Westervelt, so you bring everything to one side, to exhibit sort of the quasi-linear character of this equation. Then you obtain a speed which looks like that. And this is a heuristic again. This is not solving our initial equation or anything. But at least it gives you the idea that, okay, if you want to the speed to stay unchanged on the principal level, then you might want to try that u square should be O of h, because you have a u square here. So basically you want the perturbation of that speed to be O of h. And so that is telling you that you want essentially the strong field to be O of h to the half if E square is O of h. And so the original equation, you can try to set, initial wave to be h to the half, and then the second one should be weaker than that, so h to the 3/2. But the thing is that each one of these terms has its own expansion in h. And the difference is that, well, u is oscillatory and e is not. So you assume that your ansatz is that E has an expansion in H and U also has an expansion in H. And again, you want the UJs to be 2π periodic in theta. And here we make the ansatz of a single phase asymptotic solution. If you want to go to double phase, like multiple phases, this is more complicated. Okay, so again, recall we wanted to solve this equation over here with a divergence-free condition at 0. And you can observe that if you apply divergence to your equation 11, so you actually see that the difference of these two terms cancels. And here, actually, it's kind of important that we're using a constant coefficient model. I think, in principle, one could try to study a non-constant coefficient model, but that would be more complicated, also partly because of this. But so you can check that by applying divergence to here, that the second derivative of the divergence is 0 if this equation is satisfied. And so as long as you make this be satisfied by your initial conditions, then and the derivative, then that would be true always. So essentially this reduces the second equation to saying something about the initial conditions. And once you're able to say that, then you get for free the condition 12. Okay, so we can impose some initial data of similar type as before. So we want again to have a strong field with order h to the half. And we want to have the beam, which is oscillatory and is oscillating in a direction omega, where omega is a unit vector that we want to send into our nonlinearity. We assume always that our data is initially supported away from our nonlinearity. And again, we're going to assume that the first derivative of our full solution is 0, which again is going to generate a second wave that propagates in the opposite direction, but it's convenient to have this for reasons. Now, the difficulty compared to what was going on before was that before 0 was a solution of the Westervelt equation, and now it's not. So here 0, sorry, I mean here the constant is not is a solution. So here we cannot take E to be constant because the divergence-free condition is not going to be satisfied, because at some point you're going to hit the nonlinearity, and that will give you something. So this complicates things, because actually choosing your initial stationary solution is not trivial. You have to work a bit harder for it. So assuming you can somehow manage to guarantee that you have a solution to the stationary solution, that to this equation 12, then choosing the beam initially is not hard. Okay, so let's see how we can make sure that we obtain a stationary solution of our initial equation. So what we're looking for is a strong field which solves these equations. And this suggests that if curl has to be 0, then Oops, sorry. We should be setting the E to be the potential, the sort of the gradient of some function that is to be determined. And this is actually advantageous because it's in principle easier to determine a scalar quantity. So we want to solve an equation like this. You can check that is actually the Euler-Lagrange equation for a double phase functional. So this is a topic that is being studied in PDEs. So I have a reference. There is much more, and it's a very difficult sort of area of PDEs, very technical results. The point is that here we are kind of lucky in a way that. In this double phase functional, the h is the frequency parameter that is small. And once the h is small, actually things are much nicer. And then you can actually solve this equation 14, and you don't have to resort to extremely technical analysis. So if you're looking for a solution of this equation 14 in, say, some large smooth domain with some boundary conditions, then you can solve it, and you can show that it satisfies an sort of an asymptotic expansion in H. And so you basically, with reasonably basic techniques from PDEs using fixed point theorem and the fact that the Sobolev space H S minus 1 is an algebra for big enough S, you can show that you can solve equation 14 with certain boundary conditions, and you can write an asymptotic expansion for it. So this tells us that actually we can construct a stationary solution of our equation. We probably expect that a result of this nature is known to the experts, but we have proved it since we want it in a specific form. So to summarize, if we set our ansatz to be, starting with this gradient of psi plus the beam that has to satisfy certain conditions to make sure that the divergence stays zero, then we obtain initial data that satisfies the divergence-free condition, at least in a large domain. Perhaps not in all of our three, but at least in a large domain. And now recall this was our equation. So now, well, we play the same game that we played with Westervelt. So we create an ansatz of what an asymptotic solution should look like. As we mentioned, we start at h to the half with our non-oscillating field, and then we have the subsequent terms, which are weaker, and the beam starts at the next level, so at order h3 to the half. And you substitute into your equation. You set terms equal. You work hard, and eventually you find that at the leading order, which is h to the minus a half, the dispersion relation that you find, which is sort of the analog of the econal equation, is this one over here. So notice that this is a system basically, right? So this is a matrix over here. The gradient of E is a vector, and this is a vector. So this equation, what it is telling, well, for one thing, it is unaffected by the nonlinearity, which is what you would expect. Like you should expect that the first that the phase should not be altered by the nonlinearity. But then the sort of what you want is you want to make sure that this matrix over here is not invertible. So you want this matrix to have kernel, so that your principal amplitude can be there, right? So you're in trouble if this matrix is invertible, because then you cannot find a leading order amplitude. So you want a phi that will make this matrix singular. So it turns out that, well, our favorite phase that we used in Westervelt actually works here again. And so what this equation tells us is that the incoming phase is that sort of for this phase, then the matrix is singular, and the theta of U0 has to be in the kernel, which is a polarization condition. It tells us in which direction the amplitude should look. It doesn't tell us how big it is, but it tells us in which direction it looks. And so then using the next equations, the next level of equations, you find that, well, I mean, that one, yeah, so you find that the projection in the direction of the propagation has to be 0 for the first amplitude. That is saying that it's a polarization thing, so you have to be perpendicular to the direction of propagation, at least at leading order. And then for the part that is perpendicular to the direction of propagation, it gives you a transport equation that you have to be satisfying. And this transport equation depends on the nonlinearity, as was expected. So actually this tells you that actually the nonlinearity does have an effect at the leading order profile. But it is a linear equation. So we see that unlike the situation that we had before with Berger's equation, where we had a nonlinear equation for the principal amplitude, for the principal amplitude, here we have a linear equation for the principal amplitude, but the nonlinearity is present. So this is the weakly nonlinear regime. So we have the nonlinearity playing a role in the leading order amplitude. And so you can solve these equations, and you can determine U0 up to its zero mode, and because here you're always differentiating in theta, so you cannot say anything about the values of U0, or the average of U0 if you want. And so the first Fourier mode appears in the next equation. So you can check that actually the zero Fourier mode has to vanish. And so what happens is that now, if you take the leading order sort of strong field to be constant, which you're allowed to do in the situation we had before, that's only for the leading one. That's not the full. That's not the full strong solution. It's only the leading part in the expansion in H. That one you can take to be constant, and then you obtain two solutions. As we mentioned, one goes into the nonlinearity, one goes away. And you can actually write what the one that goes in the nonlinearity looks like. So again, as before, we have the leading order, which is constant, and then the beam at order h to the 3/2 has the form that you can see here. Here we're taking the leading order to be E3, the strong wave. So this is the one that was the strong field that was coming from above in the pictures that I had before, or I guess from below. And what you observe is that you have a phase shift in the various components. So here E3 is the component, of course, that corresponds to this one, E3001. So you have a different phase shift in different components. So this 0 here is the effect of what we saw before, that the nonlinearity, sort of the first profile should be perpendicular to the direction of propagation. Right, so this is why you have a 0 here. And here this tau is, it's very nice that this is giving you an X-ray transform actually of the nonlinearity, or something that would look like an X-ray transform if you measure far enough. Whereas if you compare to the situation for E equal to 0, you see that you don't have these phase shifts anymore. And so again, we have here omega 1 is propagating in, the wave is propagating in direction omega 1, which is 1, 0, 0, and then 0, 0, 1 is the E, is the strong wave. And the effect of this difference in the phase shifts is that the medium becomes birefringent. And so here, this is sort of these waves analyzed. So you can see that in one direction, you move a bit faster than the other. This is sort of the waves without the polarizers. Okay, and then there are lower order profiles. This looks horrible, I know, but so it's basically all the lower equations are linear and you can solve them. This is the moral of the story. And then, well, we want to pass to exact solutions, and turns out that if you can consider an asymptotic solution of this form, so you solve the equations for high enough order in a priori fixed amount of time, and then again with the help of the theorem of Guess, you can say that there exists a unique solution for your initial equation in a certain neighborhood, and the leading order looks so with initial conditions that we said before, and satisfying the divergence-free condition that we wanted, at least in a big enough ball. And also, well, I mean, the leading order profiles are what they are supposed to be. And then finally, I mean, the last minute, I can say that so the inverse problems is whether we can determine the nonlinearity coefficient from light that is traveling through it. So the setup is very similar to what we had before in the Westervelt equation. So we have the nonlinearity, we shoot our wave, we have the detector on the other side. There has been some literature on inverse problems for Maxwell equations. I believe this one uses Born series and this one use high order linearization. And so we can deduce that if you fix a direction to begin with, like an omega, and you fix some initial data such that all the rays that are issued from this direction will cover the ball and will eventually exit, then if you measure in your detector for long enough, so we want to measure for a finite amount of time that's sort of like 2 times the radius of this large ball where everything is happening, then you can recover the X-ray transform of the nonlinearity in the direction of omega. And so then, if you move your initial conditions around in the direction from which you probe, then you can recover the X-ray transform in every direction. And I mean, here the idea is in a way similar in that you look at your sort of leading profile, which was also what we did in the Westervelt equation, and you essentially want to use a sort of the product of cosines formula to try to extract the tau out of say the second component. Yeah, I mean, this gets a bit too technical maybe, but yeah, the point is that you have this sort of you have this expression that involves the X-ray transform, and involves a cosine. So basically what you want is you want to multiply by another cosine of this quantity and integrate. And once you do that, it turns out that at leading order you can extract the X-ray transform. Okay, so I think I'm going to stop here. Thank you.
Thank you very much, Nicholas, for the very nice talk. Are there any questions or comments, please? Please feel free to unmute yourself. Any questions or comments, please?
Hi, I have a question.
Mhm.
Very nice talk, Nicholas. I had a quick question, I think around slide 24 and then later also. You mentioned this like a kind of coupled system for d theta squared u.
Yeah,
Based on this,
here,
like,
right?
yeah,
Yeah. Mhm.
or d theta u naught. So the way that this like nonlinearity ends up showing up in this linear system reminds a little bit of like this lax pairs approach to solving nonlinear, like certain types of nonlinear systems. Is there any relationship?
How did you say it?
The lax pairs approach to solving. So,
Oh,
for
I'm not
example,
aware.
for example, like if you have a KdV system, you can decouple the solution into two linear systems,
Mhm.
where one of them involves the initial condition, kind of like in the same way. It serves as a potential, for example, for a Schrodinger equation, and the other one propagates the solution. So, but I don't know if there's any kind of moral.
It could be. I mean, I'm not aware actually. So, I mean, something like that, like a behavior like that, somehow it was it has been known as in like in if you look at papers of Rauch from the 90s and so on, like they because they did deal with systems like first order systems. And this actually does appear like that you have to like you obtain some equations for the polarization, like some a projection on a certain space has to satisfy an equation.
Mhm.
This kind of behavior does show up. I mean, I don't know if it's the same. It could be.
Okay,
I don't know.
okay.
Hi, this is Margaret Cheney.
Hi.
I noticed that the experimental video you showed, it seemed as if there were sort of bright flashes within your test cell, almost as if they were like bugs flying around. And I'm wondering,
Oh.
does the mathematics explain this? I'm sorry if you said this and I missed it.
No, I didn't. I don't know. So I must say that I found this video after we had sort of put the paper out. So that was not something we were looking for. I didn't think about it. Actually, I don't know. I think Plumman had a different video that he showed at some point. I don't know if that was a thing there as well. But yeah, I actually haven't thought about this. I don't know.
Yeah, thanks.
Yeah, I don't know if there is something mathematically interesting going on, or it's just an artifact of real life.
I mean, they were changing the voltage, and changing the voltage changes the intensity.
Yeah.
But if you talk about some quick flashes,
Yeah, I mean, I can.
that's not part of this. Data.
Let me see. So, you're talking about these little things?
Yes, exactly. Yeah.
Oh,
Oh.
to me, that look like feathers, to be honest. I don't know. It doesn't look like light to me. It looks like more like dust or something like that.
Yeah, probably.
Yeah, could be. Yeah.
Yeah, I don't know. That's a good question. Yeah.
Thanks.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? If not, thank you very much, Nicholas, for the very nice talk. Thank you so
Thanks
much.
for the
Thank you very much,
invitation.
everyone, for coming. Thank you.